All right, are we live?
I think we're live. I think it
I
says the
think we're
stream is
live.
live.
Yeah, we had
Yeah.
some minor technical difficulties that just kind of, what they say, if the definition of crazy is to try the same thing again and expect a different outcome, and that's exactly what happened. So,
I think before we start, the conclusion that we can come to is that computers were a mistake, and all of us are responsible for these terrible things. And
yeah, now
oops.
that we're going to give them all brains and call it AI,
Yeah.
who knows what's going to happen. So, anyway, let's get to reality here. So, thank you, everybody. I know today is the last day for J Champions Conference. I think there's one more after you. So, thank you for all those who have been watching, and I'm here to introduce Holly, my colleague. Holly and I have spoken before, different topics, and I think I've actually seen this talk before, so I'm super excited to see it again. Lots of cool stuff here. So, yeah, here you go, Holly. And if there's any, I don't know if you want me to interrupt you with questions or how you want to handle questions.
Yeah, let's keep it let's keep it interactive. So yeah, feel free to interrupt.
All
And
right, the stage is yours.
thank you. It's as Eric mentioned, I've done this talk before, but oh no, the stage is yours.
Yeah.
Computers,
Yeah, I don't know what
terrible
happened. I
mistake.
clicked the remove me from the stage and it removed you.
Okay, hooray. Yeah, I've done this talk before, but always in sort of like a 40-minute slot. And the promise of this talk is to go into all of the secrets of Quarkus, which is a lot to fit into 40 minutes. So it's nice to have a slightly more relaxed time scale. But I want to start not by talking about Quarkus, and not even by talking about Java. I want to start by talking about Rust. And I know this is the Java Champions Conference, the J Champions Conference, and so obviously, all of us speakers are really invested in Java and we're really fond of Java, and it's an incredible language. But I think sometimes we do look over the wall a bit at and see some of the new stuff that's coming and go, oh, should I be doing that instead? Could that maybe be better than Java? And certainly I've had some of those feelings about Rust, and I've kind of looked, and everybody says Rust is such an efficient language, and efficiency is one of the things that I really care about. But the good news is, although I'm going to talk about Rust a little bit, I'm not going to say anything very nice about Rust. So it's okay. We're all good. We're all still good on the Java side, because the sort of the starting point for my interest in Rust, and the starting point for a lot of people looking at Rust, is that Rust is incredibly efficient. So when you say what's the most efficient language, Rust is definitely up there. But that's actually only for a fairly narrow definition of efficiency, because when you start going from, oh, maybe I should learn Rust, to actually, I think I'm going to learn Rust, it can be a bit of a jolt. Because then the thing that you immediately discover about Rust is really hard to learn. And, if you sort of look on the internet, you'll find all of this stuff, basically just saying Rust, it's too hard to learn. And, it goes on, it's too difficult to be widely adopted. And you can really see this actually when you read articles by people who really love Rust. So this article, for example, the headline is "Why Rust is Worth the Struggle," which kind of makes you think, oh, yeah. If that's what the friends say. Oh, you're
Yes.
back.
Yeah, I'm back because there's a question. Someone is
Oh,
saying,
hooray.
and I know you have the answer to this somewhere, and I don't know if you're going to get to it, but
I don't know. So that is a very good point. So C C is the most efficient language. Rust is pretty close. So I think Rust comes within about, again, it depends on your benchmark and that kind of thing. Rust comes within about 2% of C, on the sort of the we have run micro benchmarks against every language paper that got shared quite widely. So you're right. C is the most efficient language. Rust is very, very close. And again, I think it depends. It depends how you define efficiency, because I think Rust has so many benefits in terms of the safety, that if you include safeness in your definition of efficiency, which a lot of people wouldn't, sometimes they're actually the opposite. then Rust comes up near the top. So yeah, even the fans of Rust are like saying it's worth the struggle. There is a struggle there. And in this article, they said things like, well, people will approach Rust with trepidation, and it's got this notoriously difficult learning curve. And this is my favorite bit of reading that I did about Rust. Rust is the hardest language up to that time I've met. I think this shows that they didn't try and do anything in Chicken or one of those languages, but basically Rust is hard. And what's interesting is if you look into it a bit more, some of the things that people really like about Rust, some of the things that contribute to the efficiency of Rust, are also the things that make it hard. So just as one example, one of the things that, people who are telling you how great Rust is will say is that Rust doesn't have garbage collection. This is actually only half true. Rust does have garbage collection. It's a reference counting implementation of garbage collection, which a lot of people don't count as garbage collection. But what happens if you take Rust, that famously has no garbage collection, and you add in a garbage collector? Well, at this point, of course, you've done something terrible to the language and changed the character of the language a little bit. But what happens to the efficiency? Well, it turns out that if you strap in a garbage collection, a tracing garbage collector, into Rust, and then you get people to do programming tasks, they're much more likely to complete the task, and they will complete the task in about a third as much time. So the people using Rust become much, much more efficient if Rust becomes a bit less Rust-like. And so then again, sort of broadening your definition of efficiency, maybe Rust isn't actually that efficient. And so we've got another question about what kind of app I've coded in Rust. So for me personally, I have to say, my knowledge of Rust is entirely theoretical. I sort of looked and decided it was hard and didn't actually go further. For that study where they added garbage collection, I'm not sure what they were doing. I suspect it was a fairly simple programming task that they were doing. But when we're sort of thinking about the efficiency of Rust, I think, really we have to think about efficiency along multiple axes. And so one axis, is the sort of the machine efficiency. And then the other one is the human efficiency. And with Rust, there's a fairly strong trade-off between these two, that Rust is incredibly efficient in terms of the machine efficiency, but that comes at the cost of the human efficiency. And this trade-off probably isn't too surprising to most of us. This is a really classic trade-off of, do you want your people or your machines to be efficient? But one of the questions, I've been sort of asking is, actually, do we have to accept that trade-off? It's a classic trade-off, but does that mean it's always true? Can we do better? Can we have our cake and eat it too? And very conveniently, since I work for Quarkus, I think part of the answer is actually, yes, we don't have to accept this trade-off, and we can do a lot better, because Quarkus is pretty efficient in terms of its machine efficiency. It's not like Rust, but when you compare it to other Java frameworks, a Quarkus application will start much faster. So Quarkus compiled to a native binary with GraalVM will start in 14 milliseconds, which is faster than a light bulb. It's instantaneous as far as the eye can perceive. Quarkus on OpenJDK, it's still really fast, so it's under a second, and my head is very inconvenient. But you can see if you have, your traditional cloud native stack that is not Quarkus, you're looking at about 4 seconds. So that's just for a REST application. But perhaps what I think is probably more significant is it's very efficient in terms of its overall resource usage, which means that Quarkus applications have high deployment density. If you are deploying to the cloud or somewhere where your footprint actually matters, where how much hardware you're using matters, which realistically in any kind of multi-tenant environment is all of us, Quarkus applications can be packed in much more tightly onto the same hardware than your other Java framework. So here, this illustration is showing how tightly you can pack in Quarkus native applications. Quarkus on JVM has a lower deployment density, but still much, much higher than the other framework. And the thing about this is Quarkus is doing better than other Java frameworks, but it's also competing with the other languages now in a way that historically Java hasn't really been able to. So with Quarkus, you're beating Node.js on its deployment density, which is something, of course, as a Java developer, you always want to do. Historically, we haven't even been able to do that. And you're getting pretty close to something like Go that a lot of people really like for its efficiency, for its deployment density. But this probably brings us on to another classic trade-off, which is throughput. So we had an independent organization do some benchmarking. And if you have your other stack, you get about 3,500 requests per second. And because Quarkus has this really small footprint and this really fast startup time, you might expect, I've seen this before, there's a trade-off. And sure enough, with Quarkus native, you do see a bit of a trade-off. So you have a smaller memory footprint at the expense of lower throughput. But things get more complicated when you look at Quarkus on JVM. So it's winning in terms of startup time, it's winning in terms of memory footprint, and it's also really, really winning in terms of throughput. But just sort of reiterating for the native compilation, we have this trade-off, as we would expect, this classic trade-off. With native, we're prioritizing startup time and footprint. When we go look at Quarkus on JVM, though, it's different, because all of a sudden, we don't have the trade-off at all. So again, the line was too long. My head is in the way, but you can see it's like close to double the throughput while also being better on startup time and footprint. So we sort of, we expect that performance is all about trade-offs, that computing is all about trade-offs, and here there is no trade-off. It's just better. So instead of having this trade-off where you have to choose, it's the, cake and eat it too scenario, that you're doing better on both. And so instead of having this zero-sum game, instead we're in this model where we have a double win, which is really cool. And I think, we should always be looking for these double wins. Now, this analogy of the seesaw, and, instead of having to choose, we can fold the seesaw in half. You may think, well, that's not very realistic. That's not how life works. And that's definitely not how seesaws work. I have seen seesaws. But maybe you just didn't search hard enough, because you can actually buy seesaws that fold in half. So that's the sort of why is this interesting? Why is this cool? But then the next step is, okay, but how does this work? How did the Quarkus team break the trade-off? And I've sort of said here, what's the secret? But of course, there's not just one secret. There's not just one technique. I think what's going on with Quarkus is the accumulation of a whole bunch of things, and then some of them kind of feed each other as well. But ultimately, with all of it, a lot of what it comes down to is challenging assumptions. That's where you get the innovation from, is by identifying the things that everybody thinks are true that actually maybe aren't true, or maybe they used to be true, but they're not true anymore. And so one of these assumptions that the Quarkus team challenged is don't be dynamic, which I find really interesting because I find it quite counterintuitive. Often we're sort of taught that being dynamic is what we should be going for in how we program and how we design. But I think we need to be pretty selective about where we're dynamic. Because historically, Java has this incredible engineering, but it was engineered for a world that's pretty different from our current world. So Java frameworks were optimized for long-lived processes. So the idea is you would deploy and then that would stay up for like 6 months. It would stay up for a year. You did not shut that thing down because it was so painful to start it up. And as well, the relationship with the ops team was that you tried to avoid talking to them. And, you definitely tried to avoid asking them to do a deployment. So deployment was this really rare event, which is why your processes had to stay up so long. But, of course, even in the old world, it doesn't really work to have software that's completely static for a year. The world changes, environment changes. You get CVEs, you need to do patching. So everything was designed to allow this late binding, to allow you to change some dependencies or to allow you to reconfigure the application without a restart. So, the idea is that you can be changing the engine while the plane is flying. That's really clever engineering. That's maybe not how you always want to be operating. And so we have this application framework, well, all of the application frameworks really were optimized for dynamism. They were optimized to allow you to defer decisions, to change decisions while the application was running. But of course, that has a cost. And what makes this cost kind of frustrating is that now, we run in the cloud. Cloud applications are immutable. If you want to change your cloud application, you're not going to be SSHing into your instance. Well, hopefully you're not going to be SSHing into your instance. What you're going to be doing is rerunning your CI pipeline and then pushing the new container up to the cloud. And the nature of containers is that they're designed to be immutable. Like, you could change it at runtime, but you really don't want to be doing that. You don't want your Snowflake customized containers. You want them to be coming off the assembly line. And so then that means that all of that dynamism that you're paying the cost for, you're paying the dynamism tax, and that dynamism is completely pointless. So what does this dynamism look like in a JVM, in a Java application? Well, we tend to think that for our Java application, quite a lot happens at build time. And so there is a compilation process where bytecode is assembled. And then there's also a sort of a packaging process. So in that packaging process, your Maven or your Gradle or whatever your build tool is will take your compiled bytecode and it will put it into an archive. Everything else that happens to get that application up and running happens at runtime. And there's quite a lot of that. So the first thing that will happen is loading and parsing all of the config files. So it will look for the YAML files because, it's 2025 and everything is YAML. It will look for the XML files because it's 2025 and XML really hasn't gone away. It will find all the properties files. It will look at all of those. Then what happens is most modern libraries that are non-trivial will do some kind of class path scanning. So they'll try and discover the annotations to adjust the behavior. They'll try and load and unload classes to see what's on the class path so that they can control what features are enabled. Once that's done, then the libraries will be able to construct this meta model of the world. Once that's done, then we can go on to the stuff that really feels like it should be properly dynamic, like starting thread pools, IO, that kind of thing. And only once all of that is done is the application ready to do some work. So what happens if you start the application more than once? All of those steps need to be done every single startup, even though the answer hasn't changed because we're in a container. And so it's kind of like a goldfish model of application startup, that it has no memory. It just has to keep redoing the same work every single time. And this has a big impact potentially. So if we look, for example, at Hibernate, which is one of the things that really made the Quarkus team start thinking about this, because they were looking at what Hibernate was doing to start up. When it starts, Hibernate will try and bind to your JTA provider so that you can have transactions, because of course you want transactions. The way it does this is using Java reflection. So it will do a class 4 name on the most likely JTA implementation. If that doesn't work, it will do a class 4 name on the next most likely one. If that doesn't work, it will go down to the next one in popularity, and it will keep going through the list until it's, trying the really sort of obscure JTA implementations. Each time it does that reflective call and fails, you will get a class not found exception that has to be constructed and thrown. It turns out there are 129 JTA implementations that Hibernate knows about, and it potentially has to go through that whole list every time it starts, which is expensive. I'm sort of using JTA as an example here, but this happens for a lot of internal service bindings where it's trying to bind to it dynamically. That affects the startup time, but there's also things that affect the footprint. So, for example, Hibernate has classes that are relating to specific databases. So, for example, with if you're not using Oracle, it will load all of the Oracle related support classes. And then at some point, it will work out, oh, actually, these aren't being used. I can optimize. So the JIT will spend time unloading these classes. And so that will save some memory, but at the expense of some extra work. But by that point, it's too late. The high tide memory was already set to that higher point. And again, there's a huge number of these. So with Oracle, for example, Hibernate has 500 classes that allow it to support Oracle, which are completely useless if you're not using the Oracle database. And these get loaded every single start, even though if it's in a container that will never be attached to an Oracle database. But what's interesting is it's sort of, I think it's intuitive for most people that having this stuff would affect the startup time and it would affect the footprint, but it also affects the throughput. So, for example, how the JVM works is when you dispatch a method call, so when you try and call a method on an interface, if you have several implementations of that interface, the JVM will have to do something called megamorphic dispatching, which is where it has to kind of consider each implementation before deciding which one to actually dispatch to. Megamorphic dispatching is kind of slow, relatively speaking. If, on the other hand, you only have one implementation of that interface, in fact, I think even if you have two implementations of that interface, you can do what's called a monomorphic dispatch, which is fast. Boom, it just calls it. So there you're getting a runtime effect that you are having a throughput drag because of having all the stuff that you didn't even want there. So how do you fix that? Well, the question the Quarkus team asked was, what if we initialize at build time? So what that means is that you have the same steps as before, but instead of doing those steps repeatedly, you just do them once at build time. And all you have to do at runtime is the stuff that really has to be dynamic and adjusted to your environment, like thread pools and I/O and that kind of thing. And then it means you're ready to do work much, much more quickly. And of course, if you start more than once, those repeated starts are efficient. So you can just do that tiny amount of work and leverage the work that you did at build time, and there's less wasted work, which is clearly a good thing. And another side effect of moving more stuff to build time is that if you want to do native compilation and compile to a native binary with GraalVM, a lot of the legwork for that has already been done because it's already been moved to build time. And so you get this much friendlier experience when you're trying to compile to a native binary. So that in our modern world, doing more of the work up front gives you faster startup time, as you would expect. It shrinks your memory footprint, as you would expect, and it also improves throughput, which maybe you wouldn't expect. But for this to work, there's kind of an implementation corollary, which is that the libraries in your stack have to know how to do this. They have to participate in the build process, not just the runtime process. Otherwise, what you'll get is that the Quarkus core, which does hello world, starts really fast, and every single library that you add on top increases your memory footprint in a way that you didn't want, slows your throughput in a way that you didn't want, slows your startup in a way that you didn't want. And so in order to allow libraries to take advantage of this new model where more is done at build time, you need an extensible build process. So one of the things that the Quarkus team did is make the build process pluggable. So there are plug points in the Quarkus build infrastructure that any library can hook into. And you can see, if you go to quarkus.io/extensions, you can see a whole bunch of extensions these are really integrations of other libraries with Quarkus, so that they will work seamlessly with Quarkus, but also themselves take advantage of that improved performance that Quarkus enables. So how the build integration works is that Quarkus exposes two things. It exposes build steps and build items. And any extension can make build steps and it can make build items. And the relationship between these two is that build steps are, as the name implies, they're a set of actions that your extension might take at build time instead of at startup. And the input to the build steps and the outputs of the build steps are build items. And so the Quarkus framework will look at your required inputs and you look at your outputs and then work out the right order in which to chain all of these build steps. So it's very elegant. And the framework automatically determines the correct order, and it just automatically injects the parameters that you say you need. And so the build items are really the communication mechanism between build steps. And so I would encourage you, if you have a pet library or a library that you maintain or internal library, do look at seeing if an integration with Quarkus makes sense. So we've got another question about whether Panache and SmallRye are those plugins you were speaking about. Yes. So Panache, we've got a whole bunch. Panache and SmallRye are both libraries that are able to take advantage of that Quarkus moving stuff to build time. And they do it in slightly different ways. So SmallRye is available outside of Quarkus. JBoss also uses SmallRye, for example, but the Quarkus SmallRye extensions make sure that SmallRye works in the most optimum way with Quarkus, and that, so they give you that integration, they give you that Quarkus value add. Panache is a little bit different. Panache is a layer on top of Hibernate ORM that gets, and I'll talk about it in a moment actually, but it gets rid of a whole bunch of boilerplate. And the mechanism for doing that is really, really coupled to Quarkus. So Panache without Quarkus just doesn't make sense. Panache is something that Quarkus enables. So you probably could think about the Quarkus extensions. There's sort of two groups. One is ones where it's an existing library, but we've made it work in a more nice way with Quarkus. So for example, I maintain an extension for the Pact contract testing library, because Pact worked with Quarkus, but it didn't really work in continuous testing. So I was able to fix that. We have the library. Then you have another category, something like Panache, where it just, it doesn't even make sense. It's not even possible for Panache to do any of the Panache things without Quarkus. Great question. Thank you. And so if you really want to go into the weeds with your build items and your build steps, either because you're writing an extension or because your Quarkus application isn't as fast as you think it should be, in the dev UI, you can look and you can see your build metrics. So you can see what build steps are being produced and you can see how long it's taking. So that can be a useful debugging tool. But probably some of you, when I mentioned that, the way we fixed everything is we moved all of the work to the compilation stage, or well, technically to the build stage. Some of you will probably be screaming because for us as developers, compiling our application, building our application is something we do all day, every day. I don't care what happens in production. That's someone else's problem. I want my developer experience to be as good as possible, and that means fast compilation. So this is where another piece of the Quarkus puzzle comes in, which is that, yeah, long compilation, long build is really terrible for developers unless you have live coding. So Quarkus has live coding. You make your change and it's instantly available. And that means that you don't need to care about the compilation time because you never see it. All of your changes are instantly available. So with live loading, in order to make it work, there's a couple of different levels of reload. So how invasive the reload is, how big the reload is, will depend on what you changed. So if you just changed something like a CSS file, for example, or a SAS file, that file needs to get reloaded into the runtime, but you don't actually need to change anything else. So that's just a file reload. If you did a slightly bigger change, maybe you changed one of your classes, then at that point, that new class is going to need to be inserted into the runtime. And so for that, we have a JVM agent that just allows you to change your classes. But sometimes you've made a bigger change than that. So you might have added a whole new extension or a whole new library. You might have changed something that's really affect how the application operates, like a config. At that point, you'll need to do a full restart. That sounds pretty bad, but it's really fast. And this is where, as developers, we get that benefit of Quarkus starting so fast. It means that under the covers, the framework, the dev mode, can do a full restart if it needs to, and it's pretty transparent to us. And so I like how there's this sort of, I hate to use the word synergy, but there is this complementary nature between these two things, that the fast start that seems like maybe we don't want it because it makes build time slower is actually the opposite. The fast start enables live coding, so it makes development faster, not slower. And I think making development faster is really important because when we think about, at that sort of slightly higher business level of like, where does the cost come in making software? Most of the cost in making software, at least unless you're doing AI training, most of the cost in making software comes from people. And so I hate to say people are resources, but if we think about the system as a whole, actually, we are valuable, we are expensive. Our employers should, and our architecture should be trying to optimize our time. So how do we optimize our time? How do we make us as expensive people as efficient as possible? And I think there's a couple of things. One is idiot proofing. Make it really hard to get wrong. And so Java helps us a lot with this. So we have things like strong typing, we have garbage collection. The other thing that's really important for human efficiency is feedback. Feedback makes us happy. That type feedback loop makes us happy. And it's something that, for our manual testing, for our automatic testing, for our debugging, we need that type feedback loop. And then finally, typing is not the slowest part of being a developer, but doing less typing is always welcome. So when we think about how our stack can contribute to these, as I mentioned, I think just being on Java gives us a lot of that safety. It gives us a lot of that idiot proofing in terms of the strong typing, in terms of the garbage collection. We don't have to worry about crashes. The developer mode, the dev mode, the live coding gives you that tight feedback loop for the manual testing. And this idea of making us as developers as efficient as possible, which makes us as happy as possible, is a really important part of the Quarkus philosophy, and we call it developer joy. And there's a few things that are part of this. One is that live coding that I mentioned, but there's other things that we can do as well. A big enabler of the developer joy is indexing and exposing that index. So most libraries, most frameworks, when they're doing their frameworky thing, what they need to do is they'll need to operate off annotation. So they'll find all of the classes and all of the interfaces or methods or fields or whatever that are annotated with some annotation. And then they'll also often use the Java class hierarchy. So they'll find things that implement some interface or extend some interface. And because this is so fundamental to how almost every modern non-trivial library works, you would hope that this is something that would be built into the JVM. It is not. So even though we have the reflection package in Java, there's nothing in the reflection package that actually helps us with this. I mean, we can do it, but we don't have the one-liner to actually do this. So one of the things that Quarkus provides is a tool called Jandex. So Jandex is Java index, and what it basically enables is offline reflection. So it means all of those cool things that you can do with reflection, you can do without actually using reflection, which is slow and expensive. Because as soon as you have that index, you can do all sorts of things, and you can go back to challenge some of these assumptions about what developers have to do. Because a lot of the things that we as developers assume we have to code are actually left over from when we didn't want to do these things with reflection because it would be too expensive and too complicated to debug and that kind of thing. So this is one of my favorite examples. It's a trivial little one, and sometimes I show this example and people get really upset actually because it's a different way of working. But when you're doing logging in Java, which of course you will do in production code, to initialize your logger, no matter what logging implementation you're using, you have to do something along the lines of, I would like to get a logger, and this is the class that I am logging. And it drives me mad, this idea that you have to tell the computer what class the logging call is in. Because I'm a developer, I copy and paste that and I get it wrong some of the time. The computer knows what class this is, but just because of how Java works, you can't just say it's static, so you can't say this, and it's a little paper cut of irritation. And so what you can do with Quarkus is, instead of having to tell the computer what the computer should already know, you can instead just call a static method on log, and it will work out what class it's in, which is really nice. And I think this is a really important general principle, which is, don't make people tell the computer what the computer already knows, because it's annoying and it's error prone. And I think, like I mentioned, I think this makes people uncomfortable. And I think one of the reasons that it makes people uncomfortable is because a lot of us have this kind of habit and this idea that, we mustn't be dynamic because, it will be too expensive to use reflection. But because of how Quarkus is working, that cost has gone away. Or rather, that cost has been moved to build time, where it's totally okay, because we don't even see it. So how that little logging bit of magic works is it uses Jandex to find everywhere where you have called the log class. In those places, it will work out a static field, or it will insert a static field that it calls $logger, but it doesn't really matter what the name is. And then when you call log.method, it will replace that with logger.method. I did actually check the positioning of myself over my slides, and I thought I found everywhere where I was cutting myself off, but clearly I was not. And, again, this happens all at build time rather than at runtime, so the cost is totally okay. So what you get at the end of this is, your human readable code was the log.info. Under the covers, you have the old code, but it was generated for you at build time. So that's kind of a trivial thing, but we can do much more significant things. So one sort of irritation with Hibernate is it saves a great deal of work, but you still do have to end up writing quite a lot of boilerplate queries and that kind of thing. And you can't, in normal Java, you can't inherit these from a superclass just because of how Hibernate works. So, for example, a normal Hibernate repository class might look something like this. And so, you have your list method and you have your stream method. And what Quarkus allows you to do is replace all of that boilerplate just with an interface implementation. That's the repository pattern. It's something that will be familiar to people using Hibernate. So you have your data access object. Another thing that Panache enables, which I really like, is that you don't even have to use the repository pattern. I never like the repository pattern because you seem to be spreading knowledge of your entities into two places. You've got your entity and your repository, and some people like it, and please, if you like it, do continue using it with Quarkus. But the other thing that you can do instead is you can have the active record pattern. So all of your brains are on your entity, which would be a bad thing, except that actually you don't need very many brains because most of it is boilerplate that you can just inherit from the superclass. And this idea of I don't want to have to type out loads of boilerplate. Can I have it on my superclass, please? Is something that we're quite used to with Java. But historically, with Hibernate, it just hasn't been possible. So, for example, if you imagine that you were going to try and do this without Quarkus, you might make your generic entity superclass, and you say, okay, I want to implement on my superclass a list all method. On your signature, you're kind of okay because your signature can be generic, and you can even use question mark in the right place and that kind of thing to get it a bit more tailored. But what does your implementation look like? Because of how the database access works, you have to hard code your entity type in the query, but you can't do that because it's in the superclass. So it's not possible to have this generic implementation. So again, here with Panache, what we're doing is we're taking advantage of that ability to do quite deep code introspection at build time. So when we see that you're extending Panache entity in your class, not in the superclass is just a marker. In your class, we inject those operations so that you don't need to type it. And the advantage of doing it this way as well is in your debugger, your code makes sense. And so I just love this because, we have this idea that there's a trade-off between machine efficiency and human efficiency, and, often there is, but there doesn't have to be. So the machine efficiency of Quarkus enabled that offline reflection pattern, which then enabled human efficiency. So we broke the trade-off. But, some of you probably still will be looking at the screen going, No, 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 never, never, never. I've used magic before. I didn't like it. I don't trust it. I want to do things the hard way. And I think, that's totally fair enough. And that's a really important principle that we have in Quarkus as well, is these are available if you want them, but the magic is always optional. If you want to do 100% standards-based application that, doesn't use any of those things, that's fine. And another really important guiding principle that we had was that, we want to make it so that it's efficient for all of the use cases. We definitely didn't want to do something where it looks really great in a demo, and then as soon as you kind of step off that golden path, you have to fight against the magic, and it makes everything much harder and much worse. So we really wanted it so that the magic would be optional. It would help you if you used it. Even if you used it, it wouldn't hinder you ever. So, again, it's this idea that we want to be optimized for using in production. We want to be optimized for real world usage, not just like looking cool in a demo, because that doesn't really help anybody. When I talk about why Quarkus is faster at runtime, one of the things I talk about is doing more at build time. That is definitely an important and interesting contributor. It is not the only reason that Quarkus has high throughput. One of the important architectural features of Quarkus is it has what we call a reactive core. But often, when I say reactive, people kind of go, ooh, and they kind of sidle away, because reactive programming is wonderfully efficient. It, again, going back to that trade-off, it's really efficient. It really hurts your head. It's not really suitable for mere mortals, I don't think. So, you want to take advantage of that reactive speed up, but you don't want to expose this reactive programming model to people who just want to get on and do something. So with Quarkus, you have, for most of the libraries, you have two sets of two versions of the library. So you can use the reactive library, or you can use the imperative library. Both will be really fast. Under the covers, both will be taking advantage of this reactive core. So Quarkus builds on Vertex, but we keep that reactive core really well hidden. So, make it so that people can take advantage of reactive without actually ever having to use reactive. And this is something, again, that this type of reactiveness is something that virtual threads, again, virtual threads allowed you to take advantage of some of that without having that reactive programming model exposed to you. And here we're sort of getting some similar advantages for different reasons and through different mechanisms, although also through virtual threads. But when we think about all of these performance improvements, I've covered a lot. And so I was trying to think, well, is there some one thing that I could just pick out as like, okay, yeah, this is why Quarkus is fast. And I started, looking at some of the things. And so I started thinking, for example, that one of the core members of the team is my colleague, San Navarro, and he was kind of, in a way, developer zero on Quarkus because he was working on the Hibernate team, and he did that work to redesign Hibernate to enable booting in advance. And another colleague of mine who's done incredible work on Quarkus performance is Francesco Negro, and he's sort of one of our performance engineers, and he's made contributions to Quarkus, but also to the whole ecosystem. And then, of course, I was thinking about my colleague Mario, and he's sort of Mario Fusco. He's a bit kind of Quarkus adjacent, but he's been doing some really cool fixes. So, for example, Jackson did not work well at all with virtual threads. It would pin, so then you would end up blocking the carrier thread, and Mario enabled a fix to that. So then Quarkus with virtual threads, or well, anything using Jackson with virtual threads, would go faster. And I'm like, oh, what's the common factor? What can I pull out? And then it came to me. there is a common factor. They're all Italian. Joking aside, though, I do want to say there's a huge team of people, a huge team of very, very clever people who are making Quarkus efficient. Some of them were Italian, only some of them were Italian. And in fact, one of the things that we're really proud of with Quarkus is the breadth of our contributor base. So we've just reached our 1,000th contributor, and I haven't done the statistics, but you can see from the names here, only some of them were Italian. But I think one of the things, so maybe being Italian isn't the common factor, but I think there's a level of effort and investment into performance that perhaps is a common factor. And you can see this when you look at Francesco. He is like a dog with a bone, and the problems that he's solving are not easy problems. So some of how you do performance work is you just have, this graft where, you profile and then you shave, and then you profile and then you find, the worst bit and you shave, and you just, you gradually, you eke away at it, and you tune and you tune and you tune. But what, and this is something that, France has been super good at, is, just kind of doing that. But then as well, sometimes when you get your performance profile, it doesn't make sense. And Franz has been, again, really good at, sort of looking at those problems of like, okay, well, this profile doesn't make sense. Why doesn't it make sense? What's going on? And we had, I'm surprised by the color of that. That is green on my screen, but the colors don't really matter. We have a flame graph here, only it's all black. And we had this interesting problem where we were looking at the Quarkus results on a benchmark called Tech Empower. And Tech Empower runs on a small number of cores, or it runs on a huge number of cores. And when we ran on a small number of cores, our performance was kind of what we expected. And the flame graph looked kind of what we expected. You can see it's sort of roughly triangular. When we had a large number of cores, the flame graph did not look like what we expected. So instead of, having that sort of triangular shape, you can see it's almost like a cylinder. And so we were really puzzled about like, well, oh, yes, duh. Sorry, someone's just pointed out that if you have a green screen and you have green slides, I guess that would explain it. Yes, I have chroma keyed my content into obscurity. So, why is there this huge gap? And it was really not obvious. It wasn't, this time was being lost. It wasn't turning up in the flame graphs. It wasn't turning up in any profiling that we could do. So to figure out where the time was going, Franz and another colleague, Andrew Haley, they read 20,000 lines of ASM. And, this is where you sort of get to that, obsession as a service thing. I care about this. Do I care enough to read 20,000 lines of like raw assembler? No, I absolutely do not. So when they looked into it, what they eventually found was the thing that was triggering the problem was this, an instance of check. And at that point, you should be going, because this is a common pattern. You may have seen it in like one or two bits of your code, right? And so when they looked at where this performance problem with instance of checks manifested, they found it affected like Quarkus Core and Netty and Hibernate ORM and Vertex and, the small RAI libraries that we mentioned earlier, and, Infinispan and Camel and Drools, and, OptiPlanner. And you can see that, most of these are projects that have some kind of Red Hat sponsorship. We were looking at those because, we have an interest in those projects. It's not that these were the only projects that were affected. And you can see this again with my last line, which is the Java class library was affected by this. So we have this bug in the JVM that means that when you have many cores, instance of checks are slow. The reason for this is cache pollution. So when you're doing your instance of checks, stuff is being dragged into your cache, and then the throughput of the onward code is affected. And normally when you do performance work, you get, like a 2% improvement and you're really happy. You get a 3% improvement and you're like a hero. The performance improvements that we were able to get by fixing our code to avoid this problematic instance of pattern were huge. So you can see here, we've got a factor of 3 improvement on this benchmark just by doing the workaround to avoid the instance of checks on the problematic path. But this comes back to the trade-off. So here's an example of a code fix that we did. So we did have a method that's, nice and readable and kind of obvious. And to work around this problem, we ended up with this code, which it gave us 30% more throughput. But you always know when you look at the PR for something and the developer is apologizing for the code change, that there's something funny going on. So, you can see that we did this because it made our code faster, but the developer says, I'm not a fan of the fix. This is non-idiomatic. It's difficult to maintain. So again, this is going back to this idea of the trade-off that as developers, sometimes we have to write code that makes us inefficient so that our consumers, the people using Quarkus, can get that machine efficiency. So the Quarkus team do reactive so that you don't have to. The Quarkus team write this kind of code so that you don't have to. So yeah, Quarkus team write reactive code so you don't have to. We work around the type pollution bug so you don't have to. But the other thing about efficiency and this kind of optimization work is, with this one, I should say as well, actually, that the type pollution bug, if you would like to look more about it, there's a great talk called Cracking the Scalability Wall that goes into a lot more detail than I have. And there is a JVM bug for this that had been open for ages that I think we didn't, most of us weren't running on 32 core machines. We weren't running on 64 machines. I don't think anybody realized how serious it was. And now that the JVM team realized how serious it was, they've accepted a PR. I think it was again from Andrew Haley. And so in future versions of the JVM, this is fixed, but that only helps people on future versions. But the other thing with performance is sometimes you get like that aha moment and you make this amazing change. But quite often performance work is paper cuts in both directions. And it can be kind of hard to even see like if you're getting paper cuts or fixing paper cuts. As you would expect, we run regular performance analyses. We do, performance regression testing, and then we run it through a set of statistical analyses to, identify are we getting better or worse. And if you look at this chart, just on the bit that I've shown, it looks like our performance is getting better. Lower is better. And our analysis also thought performance was getting better. But then Matt Rabel came to us and said, your performance is getting worse. They were like, computer says it's getting better. But then we looked into it and we realized that what had happened is when you look at the rest of the chart, we had a regression. So you can see performance is sort of bumping along and then it gets worse. And then we fix it. But that masked the fact that even after fixing the regression, we were worse than we were before the regression. So the statistical techniques that we were using, this parametric change detection algorithm, meant that the big regression masked the smaller regression. So it's tricky stuff. It's subtle stuff. And I think it seems really obvious to say, is your performance getting better or worse? It's not always. But the good news is, once we identified the problem, we were able to fix it. So you can see again, you've got that kind of aha moment where in one release, we had sort of a whole bunch of config related performance regressions that had crept in. Roberto did a blitz and the performance got way, way better on that release. And again, the way that he was able to make the performance better is by challenging some assumptions. So for example, in English, we read left to right. If you do an equality comparison in Java, it will go left to right. But if you think about how we namespace config keys and how we namespace lots of things, we tend to have the least interesting part of the namespace at the left if you count least interesting as most often repeated. So in this example, this is sort of a common pattern for the Quarkus config, is you might have quite a lot of repeated config prefixes, and then the interesting bit is hidden by my head, and it's just at the end. So what Roberto did is he wrote a new comparison algorithm that worked from right to left. For this case of the config, it made it way faster, which I love because it's ridiculous. That's a specific thing, but what I would suggest as, kind of there's no like one performance technique that you can apply to make everything faster. It needs people and it needs hard work. So I would encourage you, if you care about performance, to invest in your own Francesco. You can't have our Francesco because we like him and we want to keep him. And he doesn't have to be, or, she doesn't have to be Italian. But do find someone with those kinds of skills. It is a valuable addition to your team. And I know I've been going for an hour. I said I wanted the extra time, and I have taken the extra time. But I want to talk about one last trade-off, because I think this one's really important as well, which is sustainability. We tend to think of this one as another sort of unpleasant trade-off where we've got, doing the stuff we want to do or saving the planet, and we have to choose which we want. And, so far historically, we've been very much going for doing the stuff that we want to do. This isn't necessarily the trade-off that we think we have isn't necessarily the trade-off that we have. I have come up with something that I called the room model. It turned out I didn't really think seriously about the name before I gave it the name. Naming is the hardest problem in computer science, because if you Google for room model, which I did not do, the first thing that will happen is that Google will suggest that you want to spell it the conventional way, and it will show you those results. It turns out there is a Dr. Vroom who made a model, and it's not like a million miles away in terms of the domain. It hadn't occurred to me there was a Dr. Vroom who made a model. So that was the first problem. The second problem is that if you say, no, I want to spell it with the indeterminate number of R's and O's, which of course it makes your SEO absolutely atrocious. But if you do go for that spelling, instead of getting Dr. Vroom, what you get is this. And you can see I've got that bar carefully across some of these images because they are barely safe for work. If you search Vroom model with lots of R's, the internet thinks you want to read about scantily clad women and cars, and wrong Vroom model. So what I had in mind when I foolishly named the Vroom model was I was inspired by the paper I mentioned at the beginning, what language is the most efficient language. And in this paper, they have a table of results. So you can see, as the comment said earlier, C is at the top. But what was interesting was there's a column for energy and a column for time, both normalized. Those two columns are almost the same. And you can see that by eyeballing it, but you can see it more clearly if you plot it. So that line is almost straight. It's not perfect, but there's this really strong correlation between how fast a programming language is and how efficient and how sustainable and how much energy it uses, which is good because we all want to be using fast things, right? As long as they're easy to use and not Rust. So, this trend line is more or less straight. And we can see this with Quarkus. So we did a bunch of experiments with Quarkus looking at how much energy was consumed. And so in this experiment, what we did was we shoveled load into the system until it couldn't cope with the load anymore. So the length of the line is the maximum throughput. So you can see the legacy framework on native, really, really low throughput, as you would expect. We have this throughput trade-off with native. Quarkus on native, despite the throughput hit of native, still has a higher throughput than the other framework on JVM. And Quarkus on JVM, all the way to the right side of the graph, it's got the highest throughput. The other thing that this graph is showing is the energy consumption, which is the carbon footprint. Lower is better. And so you can see that longest line is also lowest. So your faster framework is also your most energy efficient framework. So this really is the Vroom model in action, which is nice because again, it means, we beat this trade-off. Instead of having to choose coding how we want to code or saving the planet, we can beat the trade-off. We can have the better framework with a better developer experience, and it's more efficient as well. And it's because these things complement each other that machine efficiency helps us gain the human efficiency, and the machine efficiency also translates into environmental efficiency in terms of energy efficiency. So it really is, it's this double win, it's this triple win. So I've been talking for 66 minutes. I've covered a lot. Here are the high level bits. When we think about efficient languages, we need to consider both the machine efficiency and the human efficiency. Otherwise, our picture is incomplete. In order to get that machine efficiency, you have to challenge assumptions. You have to get rid of waste. Only do work once. That's just common sense. Move the work to where it hurts least. So often that's going to be build time rather than runtime, for example. Indexes are amazing. Indexes allow you, they're such a simple technology, they allow you to do so much. And this isn't a one-shot activity. To maintain the efficiency, you do need continued investment. And on the human side, it's actually pretty similar. So you also need to be challenging those assumptions. That's where the innovation comes. You need to be tightening the feedback loops. So, the tighter your feedback loop, the happier your people, the more efficient they will be. And then finally, don't make humans tell the computer what the computer already knows. Oh, now I'm out of focus because I've moved too much. So with that, thank you very much. The slides are available at that QR code or that URL. And we don't have time for questions, but we have time for questions because this is an unlimited slot. We can go for as long as people want to.
Well, it's only unlimited as long as the moderator has time to stick around and answer the questions, right?
Yeah, I broke my moderator.
And I can push the buttons to say stop now. So, yeah, I think that didn't really see any questions pop up. Lots of conversation, but no real questions. So I guess speak now or forever hold your peace for those that are still hanging around. Yeah, thanks, Holly. I guess no questions. Super interesting. I know I've stolen some of the stuff for some of my own talks too, so always glad to have your stuff.
Yeah, thank you very much.
All right, thanks everybody. And I think there's one more session that's probably a few minutes already underway. So thanks for paying attention. Bye-bye.
Thanks all.